Hello everyone and welcome to this video. In this video we are discussing AS level uncertainties. So a lot of your exams may be coming up in school, in college. So I've gotten a lot of requests asking people from people asking me to basically go over this. So I'm assuming that all of you are through with the theory of this. So I'll be revising this still just to be on the safe side. And then I'll also be discussing how we think or how we should think whenever a question is in front of us and which rules do we use. So for this time being, let's just go through the rules first. So I basically break up the entire chapter and how you're supposed to deal with uncertainties into a set of rules. This is rule number 1, which says that if a measurement is multiplied or divided by a constant, then the absolute uncertainty of that measurement is also multiplied or divided by that same value of the constant. However, something to keep in mind here is this, that the percentage uncertainty and whatever applies to the percentage uncertainty also applies to the fractional uncertainty. That remains the same if a quantity is multiplied or divided by a constant. So let's say that you have something, let's say you have mass in grams, and let's say in your formula it's supposed to be in kilograms. When you are finding the percentage uncertainty of that, that's going to be unchanged because that conversion just involves a multiplicative factor, right? So something like that, or maybe if you have diameter and maybe your formula says radius, so the percentage uncertainty in the radius and the diameter would also be the same because again, the radius is just the half of the diameter. And don't worry, we'll be seeing these rules in action very soon. Let's go on to rule number 2. So this is rule number 2. This is for measurements or quantities being added or subtracted. If your quantities are either being added or subtracted, their absolute uncertainties are added. Now this could be used in a case, for example, where we want to find the perimeter. So we maybe have to add lengths, or for example, if we sometimes have to subtract masses. So this rule is going to be used in cases like that. Let's now go on to rule number 3 of uncertainties. Rule number 3, this says that when measurements are multiplied or divided for the total percentage uncertainty, you would add the different percentage uncertainties of the quantities which are being multiplied or divided. So for example, in the formula of speed, let's say if you are finding the uncertainty in the speed, you cannot directly find the absolute uncertainty there. So you must first find the percentage uncertainty in the speed, which would be the percentage uncertainty in the distance plus the percentage uncertainty in time. Why? Because speed is distance over time. So that's how this formula would work. Rule 3 is very heavily asked in the exams, as is the next one, which is rule 4. And the idea about rule 4 is very closely linked to the idea about rule 3 because for example, in some formulas, you have some things which are being multiplied and also one or two of those may be raised to a certain power. So if a measurement is raised to a power, when for example, we're using the percentage uncertainty idea. So let's say we have maybe let's say volume of a cube. So volume of a cube is L cubed. So then the percentage uncertainty in the volume would be thrice the percentage uncertainty in the length, right? So that's how that rule is applied. And then the last one is basically about representing the uncertainty. And the hint that you need to use this in a lot of the questions would be that you need to write it to an appropriate number of significant figures. So the steps for that is that you first write your absolute uncertainty to 1SF, and then whatever place value or decimal places those are, you write your principal value to that accuracy. Now to see these rules in use, we'll be going straight on to the questions. In this video, we'll be looking more at MCQs, and in the next video, we'll be looking at full-blown structured questions from the paper 2, where we'll be learning how those are assessed. So let's start with the MCQs now. Let's start with this question. A quantity x is to be determined from this equation: x equals p minus q. P is given as its principal value plus minus the absolute uncertainty, and similarly q is also given like that. What is the percentage uncertainty in x to 1SF? Now how you would do this question, or how you would do any question for that matter, is this. First of all, you think about the formula and then you think about the relevant rule. What I mean by this is, look at this formula. What's happening to the measurements or to the quantities here? they are being subtracted. So this is rule number 2, which means that if quantities are being added or subtracted, their absolute uncertainties are added. Now what this means is that if I have to calculate the principal value of x, that is very straightforward. P minus Q, which is 1.27 minus 0.83, and this turns out to be, so this value is 0.44. And now for the absolute uncertainty, delta x, I know that's going to be delta P plus delta Q. So that means I'm going to add the absolute uncertainties. So 0.02 plus 0.01, which is 0.03. And now if I have to find the percentage uncertainty, I would do delta x over x naught times 100, which is 0.44 over the, 0.03 over 0.44 times 100. And if I find this, so this turns out to be 6.8%. To 1 SF, that's 7%, which is option D. Now, what is the mistake that people make here is that they just read percentage uncertainty and they immediately think rule 3. So the problem here is that they don't really look at the formula, whereas that is the key technique, to first look at the formula, identify the rule, and then do all the working, right? So it's in that order. Let's now do another question. So this question says a student finds the density of a liquid by measuring its mass and its volume. The following is a summary of his measurements. So you have the mass of the empty beaker, you have the mass of the beaker and the liquid, and the volume of the liquid. He correctly calculates the density of the liquid as this. What is the uncertainty in this value? All right. Again, it's density. So we know that density as a formula is mass over volume, right? But not so fast. Let's think about what's actually going to happen here. Now with the liquid, we know that because the liquid cannot be directly poured onto a balance, so we first have the mass of just the empty beaker, then the mass of the beaker and the liquid. So for the mass of the liquid, we would actually subtract both of these, right? So if you think about the masses, let's call this M1, let's call this M2. So I know that M, the actual mass, would be M2 minus M1. I don't need to calculate the actual value because that's already given and it said that that's a correct calculation. But what I do need to use is that the uncertainty in M, that's going to be the uncertainty in M2 plus the uncertainty in M1. So 1 plus 1, that would be 2, right? And in fact, I would need to actually calculate the density because of the next parts. If I look at this formula, density is mass over volume. So the percentage uncertainty in rho is going to be the percentage uncertainty in M plus the percentage uncertainty in V. So how would I get percentage uncertainty in M? Obviously, I'd need the mass, which is going to be 70 minus 20, which is 50. So that's going to be 2 over 50 plus the percentage uncertainty in the volume, which is already given as 0.6 over 10. And I'll do the times 100 all together at the end, right? So when I find this out, 2 over 50 plus 0.06 times 100, this turns out to be 10%. So the absolute uncertainty I can find by multiplying this by the principal value. So 10% of the actual value, which is 5. So that turns out to be 0.5, which is option B. So this question was special because this was a combination of rule 2 here, quantities being subtracted, and rule 3 here, which was quantities being multiplied or divided. Now we'll go on to questions that test other rules. Let's now have a look at this one. In an experiment, a radio-controlled car takes 2.5 plus minus 0.05 seconds to travel 40.0 plus 0.1 meters. What is the car's average speed and the uncertainty in this value? So for the speed, we know that the formula is change in distance over change in time, or for now, if we say distance over time, doesn't really make a difference. So what's happening to quantities here? They are being added and, they're being multiplied or divided. This is rule number 3. So that's percentage uncertainty in V is percentage uncertainty in D plus the percentage uncertainty in t, right? So that's going to be 0.1 over 40.0 plus 0.05 over 2.5, and because the 100 would come with both of these anyway, I can factor that out and multiply by this once. So now I'll just plug this all into my calculator. So this value turns out to be 2.25%, but I need to give it as the absolute uncertainty, as you can also see from the options. So I'll find 2.25% of the actual value, which is just going to be distance over time. So 40 over 2.5. So this times 40 divided by 2.5 divided by 100, which is 0.36, right? But the problem here is this, that actually the value is 16, right? If you find this out, this value, that's the actual speed. So I kind of skipped over this. This is 16. But now if you think about it, you'll also have to appropriately represent this. And this is supposed to be understood even though the question does not use the phrase write to an appropriate number of SF, but this is something that you have to do. So your actual value is 16.00. Let's write it like this for now, plus minus 0.36. But understand that as a final answer, your absolute uncertainty is first going to be written to 1 SF. So this is the first SF. You look at this, is this 5 or more? The answer is yes. So this value gets bumped up. Now this is 1 decimal place. So you'll write your actual value to 1 decimal place, which just makes it 16.0. And this is the correct answer, which is option C. Right? So this, we had to use rule 3 for this question here, and then rule 5 to appropriately represent this quantity. Now let's do some more of these questions to see all the rules in action. Alright, let's look at this one. A micrometer screw gauge is used to measure the diameter of a small uniform steel sphere. The micrometer reading is 5 plus minus 0.01. So that's the diameter. What will be the percentage uncertainty in a calculation of the volume of the sphere using these values? Remember that it's important to memorize these formulas. So volume of a sphere is 4 by 3 pi r cube. 4 by 3 pi, all of this is a constant, and I need a percentage uncertainty in the volume of the sphere. So I can see that ignoring the constants, there is just an r raised to the power 3. So the percentage uncertainty in V is going to be thrice the percentage uncertainty in R, right? But now the problem is this, that here I've been given diameter. So do I need to first halve this to get the radius and then also halve this, because that's what rule 1 says, right? That if your actual principal value is multiplied or divided by a constant, your absolute uncertainty is also divided or multiplied by that same constant. Well, actually no, because we are concerned with the percentage uncertainty here. So remember that multiplying or dividing by a constant does not change the percentage uncertainty, right? So even if we want to use this diameter value here directly, we know that R, or if it's written D, right? This is not a division sign. This says percentage uncertainty in R or percentage uncertainty in D. Both of these would be the same. So that's thrice of this 0.01 over 5 times 100. And if you find this out, this turns out to be 0.6%. So that's the answer to this MCQ. Let's do one or two more. Let's have a look now at this question. A student determines the density rho of steel by taking measurements from a steel wire. So mass is given here, length is given here, diameter is given. He uses the equation rho equals 4m over pi d square L. What is the percentage uncertainty in the calculated value of the density? Again, don't get fazed by this statement. Look at the formula and think about what you need to do. 4 is a constant, pi is a constant. So there's m, d square and L. And all of these are being multiplied, divided. So percentage uncertainty in rho is going to be percentage uncertainty in m plus percentage uncertainty in L plus percentage uncertainty in D. All of this so far is rule number 3. But because there's also a small square here, the percentage uncertainty in D is going to be multiplied by 2. Now this also includes rule 4. And now I just have to plug in the values. Remember again, these are in grams, centimeters and millimeters. It does not make a difference. Yeah, if I was asked to actually find the absolute uncertainty, then I would convert these when plugging into this formula. But for the percentage uncertainty, if this is in grams or in kilograms or in picograms, it does not make a difference. The same idea also applies to the lengths. So this is again just that consequence of rule number 1, because remember that converting would involve multiplication or division by a certain value, which leaves the percentage uncertainty unaffected. So for M, this is 0.1 over 6.2. For L, this is 0.1 over 25.0. For D, this is twice of 0.01 over 2.00. And all of this is multiplied by 100. And that is your answer for this part. So let's do this together. Plus 2 times 0.01 over 2 times 100 is 3.01%. So that's option D. Now the last question that I'm about to do is probably the most difficult question, I would say. Otherwise uncertainty is pretty much sequential, so you follow a couple of steps and you get to the answer. This one is slightly a bit different. This is also asked in some different ways in structured questions. So that means in paper 2. So let's have a look at this one. So this is the question at hand. The Young modulus of the material of a wire is to be found. The Young modulus E is given by this equation below. Right, so the formula for this is given, and by the way, this is something that you will study in the chapter Deformation of Solids, which is technically chapter number 6. The wire is extended by a known force and the following measurements are made. Which measurement has the largest effect on the uncertainty in the value of the calculated Young modulus? That means in the value of the calculated E. Right, so I can see that in this equation there's F, L, D and X, and all of these are being multiplied or divided. So that becomes rule number 3. So it makes sense that I would have to find the percentage uncertainties for each of these. So let's just go ahead and do that first. And you should do this with me. So pause the video and try this out on your own. And then press play to check the values. Alright, so I've done this. So these are the percentage uncertainties I'm getting. This is 0.098%. This is 3.7%. This is 0.05% for F, and this is 3.8%. Now, a lot of you would be very quick to circle this value D, but it's actually the wrong answer. And the reason is this, that if I think about the formula here, there's a reason why the question didn't just say the largest percentage uncertainty, and instead it said the largest effect on the uncertainty. Because the percentage uncertainty in E, I would say, is percentage uncertainty in F plus percentage uncertainty in L plus percentage uncertainty in X. But for D square, because there's power there, it would actually be twice the percentage uncertainty in D. So when we talk about contributions to the uncertainty, this would actually, for D, okay, not option D, but for the diameter D, this would actually become twice. That would make it 7.4. So overall, this contributes the most, and hence option B is the correct answer for this one. So these were a couple of uncertainty MCQs that help you understand the application of the different rules. Tried to make these as diverse as possible so you see different ideas in action. In the next video, you will be seeing some structured questions solved. So hopefully that will clear things up further and give you more ideas as to how the questions are to be done. So thanks for your time. Like this video, comment if you have any questions or suggestions. Subscribe to the channel for more content like this, and I'll see you in the next one.